Systems Lecture 14. Today we're going to have an introduction to Lab 2. Lab 2 will cover data acquisition, storage, and display for our O-scope. So, overview of what we're going to be doing in Lab 2 is we're going to be adding 2 channels to our O-scope display that we already created for Lab 1. So all we're going to be doing is adding in an interface to acquire and then display those values on the screen. These are the connections on the board. Most of them you've already been using for Lab 1. Power, HDMI, we talked about the JMod programming. We're going to have our buttons, and then we're going to have audio input. And then we're going to also have an audio output. Those 2 are the new parts for this. This is the architecture that we're going to build in Lab 2. And yes, it seems a little bit cumbersome in the beginning, but we're going to go through each of these blocks to talk about what you're going to be doing. And it's not necessarily going to be that much new stuff, to be honest. So, all we're going to be really doing is connecting things together that we've already learned about. So, first of all, the Lab 2 file is given, so the top level that instantiates the data path and control units, which you're going to create, are already instantiated at the top level and connected to the board through the XDC file. Lab 1 gets condensed down to basically the video function and the button processes that you created in Lab 1. And we're going to connect that to all this other stuff. So let's start going through those. VRAM, we're going to be instantiating 2 VRAMs, although this diagram only shows 1. They're the same VRAMs that you learned how to interface with in Lecture 13. We're going to be writing values to a certain address, and it's going to be 18 bits wide because our signals coming out of the audio codec are 18 bits wide. And then those read values, those values are going to be written to and read from, all at the same time. And we're going to use essentially the row value coming out of our Lab 1 code to decide whether or not we're going to write a pixel to the display. It's going to make it pretty easy. We'll go into more detail about this, but you'll notice that the output from Lecture 13, we're going to bit swizzle off only 10 bits to compare to our rows, which our row values are only 10 bits wide, which we learned in Lecture 13, or Lecture 12 actually, how to do the bit swizzling to be able to pull off part of the function. Right now you can kind of think about it. Which would you take? Would you take the upper 10 bits or the lower 10 bits? If we're rounding, typically you would take the upper 10 bits. That way you don't lose the fidelity. So we're going to basically swizzle off the top 10 bits and compare that to our rows to see if we're going to actually print a character on the screen. I built an audio codec wrapper that basically implements all the functions required to connect to those audio ports, inputs and outputs, and do all the math and do all the clocking for you. So I gave you all this code, and all you'll have to do is implement a clocking wizard, re-implement the clocking wizard 0 for Lab 1, but you'll also have to implement a new one for Lab 2. But all those values are given in the audio codec wrapper VHDL file in the comments. So still, nothing new, except how it operates, but we'll go through that in a bit. Counter, we're going to build this counter essentially to count up through our VRAM which I gave you that in lecture 11. We used it again in lecture 13 to write values to our BRAM. We've used it many times in many homeworks. All of the comparators that you see in here, and the muxes, those and AND gates, all those can be implemented with simple when statements. So don't overcomplicate it. Don't try throwing them in a process. The only thing we need a process for is the register. So anything that you see a register value, that you need a clock value or a ready signal or something like that, that would need a process to build it. This flag register, which we'll also talk about in more detail, is just a multi-bit register that we can set in clear bits. And I'll describe the functionality that we want for this lab. The rest of it is just interconnecting muxes and things like that. Connecting things we already learned about and we already know. So, talk about our data path and control, which you're going to create. The data path, just like for the keyboard and the other data path and control items we learned about, the find minimum architecture and all those, we're separating our data path and control. We're going to get status signals coming from our data path to our control unit to tell it how to step through the different states. And then it's going to, our control unit is going to send those signals back out to our data path. And if you look in the design, you'll see a few status words and a few control words, right? I see a comparison here that's going to be basic. We'll talk about this more. It's basically going to look at the value on the screen that's coming in to see if it's above and below, essentially greater than and less than, certain value on the screen, so we know when to start, basically when to start writing that channel to the screen. So that's going to be a status word coming off of there. And we'll talk about that more in detail. We also have a ready signal coming out of our audio codec wrapper. That's going to be operating just like the keyboard, the PS2 keyboard. When it's done and it has an 18-bit value ready for you, it's going to spit out a status word for a clock cycle. Plus the compare signal here on your counter so you know when to reset it. Control signals are going to drive things in our data path coming from our control unit. We're going to have one control bit going into our write enable. And then we're going to have 2 bits going into our unsigned counter, which you already know how to use those control bits anyway. 0, 1 to count, 0, 0 to hold. So there's going to be 3 status words and 3 control words in our system. So let's talk about this audio codec wrapper and how that actually works. The audio codec wrapper is built and interfaced so all you have to do as a user is look for similar signals that you learned about in lecture 12 and homework 8 for the PS2 keyboard. Essentially, these 18-bit values on the audio codec will be continually updated, but when they're ready for you to latch that data into a register, let's say, into this register, you'll get a status word, a ready signal coming off the codec wrapper for 1 clock cycle only, just like the signal, the status word coming out of our PS2 data path. On that ready signal, I gave you some code in the lecture that actually takes that, latches it in, and then loops it back to the output. So that way you can test your codec wrapper, make sure your signals are hooked up right, and that's partially gate check 1, which is to implement your lab 1, implement those clocking wizards, and then hooking up this codec wrapper just to loop back on itself so you can actually apply an audio signal into your device and be able to hear it back out on the output channel. This will be a good loop back function to leave in your system so that it always loops back that output signal so you can see if the hardware is working properly. The other visual display you'll get is your Lab 1 functionality as well. So if you want more information on the datasheet, you can take a look at this datasheet. This is our ADAU 1761 audio codec wrapper that is connected to our system. It's an 18-bit, where we're only using 18 bits. It's actually a 24-bit stereo audio codec, analog to digital and digital to analog converter. There's lots of information in here that you won't have to know because I built this wrapper around it to basically convert it to a 48 kilohertz signal coming in, and it'll be 18 bits wide. It can run up to 96 kilohertz, but right now we're just running at 48 kilohertz and 18 bits. And again, here's a loop back process. Basically, if ready, it's going to put L bus out and R bus out, the two left and right channels, loop it back on itself. Otherwise, set it to 0. And again, you'll be applying an input here, and then you'll be able to hear that input coming back out here if you set up the loop back right and you set up your clocks right. Again, part of that 8 audio codec wrapper, we have this signed to unsigned data. So we're going to be taking in standard logic vectors, and or signed values coming out of our audio codec, but we want to make them so they'll fit on our screen, which is completely unsigned values. So we need to be able to convert that. Seems a little cumbersome when you look at these values, but it's actually very simple conversion. So this shows 18 bits, a negative value, right? It's negative 131,072, and that's 1 with basically 17 zeros after it, and that's in 2's complement. And then a negative 1 is all 1s, right? 18 ones, a 0 is all 0s, and a 1. And then the maximum positive value for 2's complement is 131,071. To do the conversions to these unsigned values, which goes from 0 to 0 with a bunch of 1s, that's 131,071, which is the same as over here. And then 1 with a bunch of zeros after it is 131,072. Basically, to do the conversion, all we have to do is add 1 in with 17 zeros after it, or adding 131,072 to be able to convert this to unsigned values. So if I wanted to convert 0 so if I add 1 with a bunch of zeros after it to this value, I get 262,143, right? All we're doing is adding 131,072 or a 1 with 17 zeros after it to be able to do that conversion from signed value to an unsigned value. So I add that to this, we're going to get 0 out of it, right? If I add 131,072 to that value in unsigned, you're going to get 0, basically moving it up on the bar. Because on our oscilloscope screen, it goes from 0 to how many rows? 525. Right? And again, we're going to stick to a specific data path port map. This is the port map that you're going to use for your data path. There's also one in the pack file that shows the control unit as well. But initially, the first thing you're going to do for this lab is you're going to download all the code that I gave you and create a data path. This is essentially going to be where you're going to implement most of the code except for the control for your system. The last thing we want to talk about is our flag register. That's that right there. It's basically a multi-bit register that can set and clear the values based upon this truth table, right? If not the rising edge of the clock, it's not going to do anything, right? If reset is 0, it's going to reset. If not the rising edge, it's not going to change the output. So it's just like a register. On the rising edge, if we are setting or clearing, and that's going to be bitwise set and clear, it will set the value or clear the value based on those set and clear value register values. And then if they're both 1, that should never happen. That's a don't care condition, so you can decide what you want it to do. Ultimately, you're going to have n minus 1 down to 0. I have a few specific ones that I want you to utilize, and I'd probably stick with, say, an 8-bit, something that would work well with a computer, a processor that we're going to drop in later. 8 bits is always good. Again, so these, the flag register, and then all these external buses, and these external addresses and write enables and other signals are going to be connected to our Lab 3 setup. Those are some of the soft core connections. Notice on these L bus and R bus outputs and inputs, they're all 16 bits wide. That's because our processor typically likes powers of 2. So these 18-bit L bus out those values to be able to hijack those signals and throw them into our soft core. We're going to concatenate them or shorten them or round them up by 2 bits. So we're just going to lop off the lower 2 bits and output them here. And then later we'll actually take an input from that and be able to apply that to our VRAM in our memory later. Last thing we want to talk about is package files. So package files are basically which we already learned about, where you can put together all your component declarations for your system, all Lab 2 components that I give you and you're going to be creating, like for the data path. They're already declared in here. The FSM is declared in here. All you have to do is implement those files. But this allows for more modular code. It's sort of like a header that includes all the declarations. So if you update multiple files, you can do it all in one place. These are the files that I give you, and you'll download each of these right now and install them into a Lab 2 project and start a Lab 2 project. We're going to take a look at each of them. We have the Lab 2 top level file. Lab 2 just incorporates our data path and control units and then implements those. We have a test bench for our Lab 2 data path. That's going to set the clock values and set up an alternating bit clock input so you can do a little bit of testing on the data. And then it resets the signal, and notice it actually does set a couple control words, right? First one resets, and then after that it counts up. and go back and look at what the other one means from the diagram. Audio codec wrapper, the only one you're really going to look at is the VHDL file. The rest of them I created and wrapped up with this wrapper. This I2S transmits the over via I2S out of that system. Then we have a V file, Verilog. That's the audio initializer portion, and then the TWI controller portion is the other VHDL file. But the codec wrapper, that's what you're going to be utilizing. Basically, it works like the PS2 keyboard. There's a clocking wizard, ClockWiz1. You're going to have to set up 2 clocks for that. Set it up after you do ClockWizard 0. We're going to need a 12.288 megahertz clock for our audio codec master clock, and then we're going to need a 50 megahertz serial communications clock. Set it up just like we did in Lab 1. There's a Lab 2 XDC file. All that makes all the connections from Lab 2 to all the necessary inputs and outputs on the board. You probably would want to take a look at this and see how that's set up, but definitely put it in your project. That makes the connections to the board. All right. One good thing that you'll find out later is you'll be using this 3.5 millimeter jack to input signals to your board. Your phone, if you have an Android phone, that's really cool, because, or even the iOS, you can download a function generator similar to this. This one is for the Android, and you're basically able to generate channel 1 and channel 2, two channels output of different waveforms. I have this downloaded on my phone so I can actually generate those signals on that 3.5 millimeter audio jack. Just for informational purposes, your audio jack is going to have a tip, a ring, tip and ring, and then the ground on the sleeve. So typically it's set up so you have your left, your right channel, so that's left speaker, right speaker, and then a ground, depending on how it's set up. That might be something you want to remember if you're actually wanting to hook that audio jack up to an actual logic analyzer that doesn't have a 3.5 millimeter jack input. So, gate check 1, due by close of business on Friday, lesson 14. You need to start a project, download all those files, drop in your video, VGA, scope face, DVD, TDMS files from Lab 1 into your project folder, and test to make sure your scope face works. And then you're going to also implement the audio codec wrapper. So there's 2 clocking wizards, Lab 1 clocking wizard, and then one for the Lab 2 project that you're going to have to implement, given the comments in the code. And then you'll drop in all your video instantiation and button processes from Lab 1 into the Lab 2 data path. And then drop in that loopback and make the connections. And it should be able to loop back the audio, as well as your Lab 1 functionality should be working if all is hooked up properly. More information on the gate check 1. Gate check 2, this will be the harder part, and we'll talk more about this later. But essentially you're going to be implementing your and this will be after the exam, so we're going to talk about that. You're going to be implementing a left channel VRAM to write those codec values into an array in memory. And writing those values, so you're going to have to make the connections for the counters and all that to be able to make it start counting up in those memory addresses, and writing those values in memory over and over again. The rest of this we'll discuss in class. But there's more on using your test benches to help you out. Required functionality will be getting a single channel on the oscope, basically a 220 hertz waveform. Need to have a separate data path and control. Your data path will also use a process similar to the counter muxes and registers. You don't want to have one massive process that does everything. You're going to also create a test bench to test your flag register and a test bench to test your control unit. So we'll have to discuss how to build your control unit. And then the requirements for the test bench for the data path. I already give you a test bench for the data path, so you'll just hook that up and get it to work once you have all the connections and show the proper outputs. There will be some bonus points for that as well. Then there's going to be a B functionality, adding a second channel, basically copy and paste one left channel to the right channel. Integrate some sort of deep bouncing strategy, and be able to move the cursors on the screen. So that's basically A functionality from Lab 1. A-level functionality, you'll actually trigger the voltage based on the captured waveform as it's coming in, move it up and down based on the level that you're triggering. And that, for the A functionality, is this right here, this functionality, where it's looking at this bus as it's coming out and putting in those values into memory, and it's looking for a trigger point where it wants to start drawing it on the screen. And that'll just make it so as you move the trigger mark down, it's going to push the signal out to the right, right? Because if it was triggering right here, this will be pulled back to the left-hand side, just like on a oscilloscope.